So cool.
Amazing.
It's amazing.
Oh my god.
Wow. This is super cool. Hello, and welcome to Stir Fried Fascination. My name is Rasmus, and I'm fascinated by almost everything. Astrobiology, step dancing, the history of furniture, Bulgarian dance moves, fossilized dinosaur poo, and Belgium. This is part 2 of an interview with John Martinis, a leading scientist within quantum computing. If you missed the first part, don't worry. It's like with Second Breakfast. You can go ahead and jump right in. Now let's get started. I wanted to talk a little bit about your sort of problem-solving style as well, and your personality. Like, is there a pattern to how you go about finding interesting problems and solving them?
Yeah, I like this question very much because I think I have a definite style. And what I like to do in science is to be working on some science and technology which has a goal. But let me tell you why I like this so much is because what you want to do in science is you want to have 10 or 20 experiments you want to do, and you want to choose the best 2 or 3 or 4, right?
Right. Okay. Yeah.
I like having an end goal because then you choose among all the possible experiments you can do, what are the experiments that could get you to that end goal? What technology you're going to build, what scientifically you're going to prove. And that way I'm better able to choose. But the one thing you always have to do, which it's taken me a long time to truly understand, is you always have to be aware that you're going to be surprised. You don't know what's going on. You're going to take some data that doesn't make any sense. And in fact, when you do the experiment where you really don't understand what happened, then it's like, well, okay, now I'm really going to learn something, and this is good.
Right. Yeah.
Right. So it's a really, I think it's really fun and interesting as a scientist trying to balance all of that.
And that was what I was thinking of as well when you were telling me that you need to have sort of a goal and that you're choosing your experiments according to that goal. I was sort of wondering if that leaves you open to surprise.
Yeah, so what happens is, you want to have a prediction of what's going to happen, and then you have to look at your data very carefully. But I would say the one negative thing about this kind of goal-oriented is that it's easy to lose sight of doing something kind of weird and missing out on new ideas. And you always have to be aware of that. And one thing we always did is we looked very carefully at what all the other people were doing in the field and trying to understand, did their data make sense in our model? And then seeing, maybe there's something weird here, and maybe we should investigate it too because we don't understand it. So there's a little bit of exploring, but it's also making sure you're still moving. I don't know. Maybe it's like when people were exploring the West in the early 1800s. You have a goal maybe to find a river or cross the continent or something, but you're moving around and finding. Then you discover things like Yellowstone, right? Which you didn't expect, right? Just by exploring around, and it takes a while. And I think a lot of science sometimes is done that way. You just have a bunch of people with a bunch of different ideas and goals, and then they kind of explore. But I think it needs a little bit more directed. That's just the way I think, and that helps me.
Yeah, nice. Do you have someone like a personality that's inspired you, like Richard Feynman or someone who's like?
I always liked Richard Feynman as a student, in the sense that the way he explained things was very unique.
For those who don't know him, Richard Feynman is considered to be one of the greatest physicists of the 20th century. He won the Nobel Prize in 1965. He also worked on the atomic bomb, although he regretted it later, and he pioneered the field of quantum computing. He was also known for having mildly electrocuted his sister, and for a tendency to fly into a rage if interrupted when playing the bongo drums. But who wouldn't? Now back to John's experiences.
Just had a good ability to explain something complicated in a simple way. And what you don't necessarily see unless you're a physicist is that he tries to explain things in a simple way that retains the correctness of the core physics, but it tries to remove all the tries to simplify it enough that you don't get bogged down in the mathematics or whatever, that you can get to something core. And yeah, I think as a young physicist, I appreciated that.
Right. Yeah. Yeah. He seems like a very inspiring figure. I haven't read so much or seen so much from him, but he does seem to be a very inspiring figure.
Yeah, so as I mentioned previously, in the mid 1980s, Feynman gave a talk on quantum computing, which was really wonderful. Now, I have to admit that I actually didn't understand it very deeply.
Okay.
And the funny things afterwards was, of course, in the Q&A and going to lunch afterward, he was totally mobbed by everyone, and rows upon rows of people standing around him. So like the professors were in the tightest circle, right? And then you had the postdocs around him, and then I was just a mere graduate student. So I couldn't hear what was going on. It was
Oh God.
but what I thought was funny, which was very motivating for me, is I knew that this was an important question. Physicists would like it. All these ideas would float around, and you'd have to figure it out. So and a large part of doing science is figuring out what are the interesting questions. And it was
Right. Yeah. Yeah.
that okay, this is and very deep. And in fact, Feynman talked about that. This is a very deep question that's still going on. So I very much appreciated that, and that motivated me, to work in the field and think about this.
Right. So, what's the most fun problem that you worked on?
What I found very fun recently, which sounds really boring, and that is how we're going to wire up our qubits. Okay, so right now we're at 50 qubits, and we connect them up and control them a certain way. And I was trying to think very profoundly how to wire up 100,000 or a million qubits and how to build that. So that has been a really fun exercise for me in the last 3 years. And it turned out that the technology that you do that, I had to invent 10 or 20 things to get it to work. And what was interesting about it is if you have 20 things to invent, but you only invent 19 out of the 20, then the whole
Yeah.
system won't work. Okay.
Yeah.
So you have to think carefully
Right.
about how to put it together. And I've been doing this for many, many years, so I was relying on my expertise there. But it was just kind of fun to just step by step knock out all the solutions and then start building and testing it. And of course, there was a lot of iteration.
But so you had to actually think sort of, if you're going to invent one thing, you have to think sort of, how is that going to affect the other things I have to invent as well?
That's right. And what's
Right.
happening is you're building a complicated system with many components. And I enjoy just kind of thinking about, well, what was the basic physics we had to do? But then also thinking about, okay, we have this big complicated system, which we were beginning to understand as we did the quantum supremacy experiment and building it, what you would need to build that system, and then kind of merging that together and figuring all that out. And of course, like I said, I like to build things, so it was nice to figure out how to do all that. But it
Right.
took
Yeah.
many years and lots of ideas that didn't turn out to be so good. But no one, this is not something that people are looking at very carefully because it's 5 or 10 years in the future. And given my situation and knowing what they were doing in the lab on the quantum supremacy, I had the opportunity and time to kind of look at it afresh and new. So I
All
enjoyed it.
right. Yeah. I was also wondering if you ever use any sort of creativity aids for sparking creative thinking, like simple example where you're brainstorming. There are also others. There's one called Scamper. There's another one called Triz. Do you know about any of these, and do you use them at all?
No, I don't.
Right.
I should maybe find out. Of course,
No.
the
Like
best.
if you got this far without them, I'm pretty sure you can do well.
I'll tell you what I do, but I the one thing you do, all scientists do this, is you explain what you're doing to other people. Okay.
Right. Yeah. Yeah.
And, you traditionally you do that by writing papers, and you also do that
Mm.
by giving talks. And,
Right. Yeah.
just talking about what you're doing, even what we're doing right now is going
Mm.
to engage my brain, and I'm going to come up with some idea
Mm.
by
Yeah.
doing that. So it's just
Yep.
a matter of thinking and explaining and going
Mm.
back and forth. And of course, you talk to other people. But I would
Mm.
say that the other thing is just to keep thinking about something very deeply. So, you have a solution and then you try to look under it. Well, why is that solution so good? And what are
Hmm.
the 10 ways that maybe you can do it differently to make it better? And,
Mm.
do that. But the other thing for me, which I find, is the best way I come up with solutions is to actually go in the lab and start building something.
Right.
And
Okay.
for example, years ago when I was younger, I would actually go into a clean room and build the qubit chips.
A clean room is one of those things in physics that is exactly what it sounds like. It's a very clean room, containing the opposite of chaos, confusion, and disarray, so you can manufacture sensitive equipment like qubits in there.
And while he was building the qubit chips, I would think about, well, how to build it better and all that.
Yeah,
For
sure.
example, this whole wiring and how to scale up and whatever. What I decided to do is just start building it. And then by
Mm.
building it and seeing how things work and just engaging your mind, you then think of new ideas. So,
Right. Yeah. Yeah. Sure. So you get your ideas while you're working at something. So that's kind of interesting. You're not sort of this Archimedes type who gets ideas in his bathtub and sort of runs
well,
out screaming eureka.
ideas in the shower, okay, but
Okay.
but I've been thinking about it for a long time, and I'm actually building things, and somehow
Mm.
all that combination of things, helps me understand what to do. And I think what happens with physics is physics trains you to always be questioning your assumptions and looking at it a new way. And maybe you
Mm.
have a formula or an explanation, but you're always looking for a better explanation that's clearer or more general or something. And physics is actually very good for you to be inventive in this way.
Right. Yeah.
And that of course is how you get trained and learn how to do these things. Well, I'm just going to give you, and I already talked about this, is how to do wirings to make many qubits. This is
Right.
not really talked about much right now in the field or whatever, but I've been
Hmm.
thinking about it for a long time, and I know it's important. And then I worked on it some, and then it's like, well, okay, I have a pathway to do something right now. So it's kind
Mm.
of happening to me right now is how to scale up qubits properly. And yeah, I'm not sure we can do it, but
Hmm.
it looks harder than anything I've ever done before. But it's not
Yeah.
that much different than five other things that looked impossible and
Right.
work.
Yeah.
You know how it is, and it's always a risk. And my point, for example, in this thing is, yeah, well, I think I can do it, but if I can't, I should at least try. And then
Mm.
what's going to happen is, if I try, I might be able to invent something that's an even better idea, right?
Oh,
So you
right. Yeah.
have to
So
get
you're
started.
actually you're not only going for what your goal is, you're also sort of going for something better that might happen on the way.
Well, and we know that we want to be able to scale up the qubits. We're at 50 or so now. We want to go to 1,000 and 10,000. Because that's going to be more interesting, and eventually up to larger numbers. And it's like,
Mm.
well, we have to learn how to do this, so let's start working on it. And
Right.
and then you have to. But the hard part is you have to come up with a rough idea of a pathway that you think you can get there. And that's kind of what's happened in the, let's say it's taken me 3 years. And it just takes time, and you have to keep thinking about it.
But what's the hardest part of inventing something? Is it thinking of good ideas, or is it selecting amongst good ideas of what might work, or is it something else?
Actually, I think the hardest thing is to be self-critical. You
Oh,
have an
really?
idea, you even have data, But you always have to be wondering, well, is this really correct? Is my
Mm.
idea good? Is there not
Right.
another good idea out there?
Mm.
And
Yeah.
as well, we're all human beings. We understand that it's very easy to not be self-critical,
Oh
and
yeah.
I'm not, and everyone's not. It's just really
Yeah.
hard. And
Yeah.
again, you kind of, I like say, I develop tools to try to analyze what I'm doing and
Mm.
if it's correct. But yeah, it's very easy to go in some direction and not realize that there are other things to do.
Oh
Well,
yeah, for sure. I have that a lot as well.
yeah, that's right. And the other thing that happens is you can see that everyone else in the field is doing something, and then you
Mm.
just want to follow the herd because you know
Right.
whatever, but that may not be the right thing to do. And again, there's a
Mm.
self criticalness to not follow everyone else.
Yeah, for sure. Yeah. Totally agree with that as well.
So you have to think carefully about what's going on. And again, I
Mm.
think physics training is quite good for you that way because that's what we're
Right. Yeah.
kind of trained to do that. And there's a
Yeah.
long history of people, breaking assumptions or doing something, discovering important things. So it's really something we know how to do.
Yeah, I've studied a little bit of everything, and for me, there's been a huge difference in studying, let's say, a semester of nanotechnology from like a couple of semesters of history, because in the physics field, people really seem to have this sort of let's break assumptions sort of thing going on,
Right.
which I really love because. I don't know why, but I think it's because I like music as well. That's sort of
Yeah.
new
Yes. Yes.
and experimental.
You're
And I
always
always sort
trying
of
to
have,
do something creative and new, right?
yeah, exactly, yeah,
And
uh,
we're doing that in science too. So
mm, yeah, exactly. And the humanistic side of science doesn't really have that as much, I'm afraid. They're sort of following traditions more, and it's important to follow a certain tradition in a certain school to get sort of accepted by the group
yeah,
and move on in your career. Otherwise, it's kind of harder to move on.
right.
So that's my experience, at least.
Right.
Uh,
Well, and I would say in science, there are fashions and fads, and you can,
yeah,
let's say you want to get tenure, okay? You should
mm,
probably just follow what lots of other people are doing to get your papers
right,
and make your
yeah,
contributions. And then once you get a little bit older and you have tenure and you do things,
mm,
then it's a little bit easier. But of course, when you're young, you're really creative and you want to do
right, yeah,
then. It's always a hard balance. And of course,
yeah.
some people who are like super creative might be doing things that would never be necessarily practical.
Yeah, yeah, for sure.
So you always have to balance these things and you have to come up with
Mm,
good ideas. I mean, that's the important thing.
yeah,
And okay,
yeah.
just have to learn how to do that. I don't, there's no magic formula for me in that way.
Mm. No, it seems to be a balance. I'll tell you a little story. I was studying intellectual history, and I was reading a book, and there was this guy who was claiming, obviously this is not certain, but he was claiming that the reason that the Arabic societies, which were sort of way ahead of us in the Middle Ages with science, weren't advancing as much as the West did in the long term. One of the main reasons was that they were more creative than we were. So they would actually invent new stuff, but they wouldn't really retain the ideas because then they would go and think of the next thing instead or the next thing, and there wouldn't be sort of a pattern to it.
They wouldn't use the inventions.
No, they would use the inventions, but let's say if there was one guy who came up with something, let's say the Earth is revolving around the sun instead of the other opposite way around, then that would be allowed. Like in a Christian society in Europe, that might not be allowed to have that thought.
Mhm.
But on the other hand, uh, that person would be allowed to do that, but they wouldn't really incorporate that into the institutions, the sort of learning institutions.
Mm.
While while in the West we took way smaller steps, but we sort of retained the few steps that we took. So that's sort of the idea that we managed to over time be more creative because even though we weren't more creative as individuals, we sort of were had more creative institutions over the long run.
One of the
Uh,
things that is interesting about this is um, when we did the quantum supremacy experiment, there was a lot of, most people liked it, whatever, but there was pushback for doing something new in the way that you're talking about.
Yeah.
And it was
Yeah.
always very funny because I personally thought, oh my God, this is this wonderful experiment for the field and it'd be great. And
Yeah.
I think a lot of people
Yeah.
think that way. But I always
Yeah.
was surprised at the pushback. We're doing something new. It's
Yeah. Yeah.
it's different. Okay, no one had really thought about this and that, and I was surprised at the pushback. In some cases, I think people they're competitive and they have to
Mm.
show their thing or whatever.
Yeah. Yeah.
I also thought it was a little bit, and especially because as scientists, we're supposed to do something new.
Right. Yeah. Exactly. Yes. Exactly.
Maybe
Um,
a lot of times it's like, well, okay, it's new, but it's not that significant, and
right.
okay, I guess that's a fine argument. But yeah,
Mm.
I kind of saw that in the recent history for me, and it's just the way it is. New ideas.
Mm.
It's new ideas take a while for people to understand.
Yeah, I guess so. I don't know if you know about Thomas Kuhn. He's quite a famous guy for. He was a historian. Well, actually, he was sort of an amateur historian. He wrote a big theory about how science works. Because it was a historical theory, I would say it's actually in reality more a theory of how science has worked.
Mhm.
But he was the guy who invented the theory of the paradigm.
Yes.
So here's a fun example. In the beginning, they thought that electricity was a form of liquid. So
Yeah.
that was a paradigm. And they were trying to make capacitors look like bottles. Well,
Right.
they didn't know that they were making capacitors. They were trying to make bottles to bottle up electricity. And during that time, there were lots of people who said, "This is kind of crazy. Maybe it's not a liquid." uh, but as a group, the scientific community still went with that idea. And sort of shunned those people who were thinking of these new ideas. And it took a long time before they could have what he called sort of a scientific revolution. Like at first, there's always resistance, according to him. Like there's always people complaining, no, we should, like, let's stick to the idea we have and let's not try something too new here. What are you doing? You're kind of crazy, et cetera, et cetera.
Yeah, and I
Yeah.
know, yeah, I know of this, and the more modern example was plate tectonics, which was not really accepted widely until the 1960s. And you see how obvious that is today. It's like, well, how could that happen?
Allow me to indulge in plate tectonics for a second. The basic idea is that Earth's surface consists of a bunch of plates moving around. For example, Europe and North America are moving away from each other at roughly the speed of which fingernails grow. That's plate tectonics in action. And it's beautiful to look at too, as you can see at Thingvellir in Iceland, which also happens to be where the first parliament on Earth was founded. Probably by some bearded Icelanders who spoke with a lisp and were exiled from Norway because they killed someone's cousin. Now back to John.
But what I like about science is that if you have a new idea and you can make predictions, it leads to better and better ideas and better understanding and inventions. So there's this feedback mechanism for good ideas where more and more things happen from that.
Yeah, that's true.
It's not just an intellectual argument. It's like, well, can someone think of 10 more experiments or 10 inventions out of that idea? And then you know that you're kind of in the right direction. But the nice thing about humans is we all have different abilities or whatever, and we use that, and then all these different capabilities people have can be used in the system to come up with the best results. And I know in quantum computing that there's some other groups that have thought of things that I probably wouldn't have thought of, but they uniquely thought of it, and then I was able to see that and use it. And having all these different personalities is very powerful for science.
Yeah. So let's see if we can get into the physics of it again. I'm curious if you ever use concepts from the quantum realm as sort of metaphors for life.
Yeah, I know a lot of people do that, and
Mm.
a very popular thing now is the multiverse.
All right. Yeah. Yeah. Yeah.
But what's funny is, I guess I'm just pretty literally minded. I find these things to be kind of amusing, but I tend not to use it. And partly it's because analogies are kind of good for explaining things, but they're never convincing, right?
Right. Yeah.
I'm careful about using analogies, but yeah, every
Mm.
once in a while I'll say something in jest or that
Mm. Okay.
we
Yeah.
make jokes about that, but
Mm.
it's not actually analogies are not good arguments.
No, but yeah, well, I was kind of interested in it because there was obviously this period where, in popular culture, you could see quantum analogies everywhere. People who were selling magical crystals would go like, "Ooh, but quantum mechanics,"
Crystals
and
actually quite a magical because the atoms stack up in a certain arrangement next to each other. And the
yeah,
crystal is actually telling you how the individual atoms are stacking up. So when you
mm.
look at a crystal, you're kind of looking at the effects of quantum mechanics.
Oh, really?
So you look at a salt crystal,
Right.
a cube looking, well, that's how the atoms are stacking up. And you look at
Mm.
other crystals, they might be more hexagonal, and that's how the atoms are stacking up.
Really? That's kind of amazing. So you can just look at like if you have a crystal like structure, you can just sort of look at how it looks, and then sort of from that draw conclusions of how the atoms are actually arranged.
Now to get a detailed thing, you do X-ray diffraction, and there are scientific,
Right? Yeah,
but you can pretty much. And this is what's great when you look at it,
that's amazing.
you're seeing the mystery of quantum mechanics. So I
Mm.
can understand why people find it has these really strange powers.
Yeah,
Because you're really looking at this fundamental physics thing,
yeah,
really
yeah.
amazing. And then if you think about, well, why are some crystals one shape or the other? You're looking
Mm.
at very, very deep physics there, which
Right? Yeah,
so I can kind of understand, why
yeah.
people feel that way. It's
So, are there any other sort of fun facts about quantum computing or quantum mechanics that would be nice to know? Sort of odd or unnecessary knowledge, but sort of fun and surprising and inspiring.
Yeah, I was talking earlier about what our quantum supremacy showed, and let me get back
Mhm.
to that. And
Right.
this is a neat thing. So, you know, up until our experiment, people knew that you could do this kind of parallel processing on a quantum computer of about 1,000 different states. Okay,
Hmm.
so parallel computing of 1,000. When we did the quantum computing experiment, instead of 1,000, it was 10 to the power 16 states. So that's 10 with 16 zeros after it.
Yeah.
And what we were amazed at is that we increased the parallel processing and complexity by from 1,000 to 10 to the 16, 10 to the 13. There's a huge amount. And the physics was just exactly explained by the normal Schrodinger equation. So we tried to test it in this totally, expanded way by
Mm.
many, orders of magnitudes, and
Mm.
everything still worked properly.
It sort of worked the same way as the small experiment did.
And we didn't know, and to change
Mm.
something by that much, how many times in physics have you changed some parameter by 10 to the 13?
Yeah. Yeah.
That,
uh,
that would be 10 trillion. Okay, so this is an economic size number, so people know about by 10 trillion,
right. Yeah.
and nothing went wrong, and everything was understandable. That to me was kind of amazing. And like I say,
That
that
is amazing.
we weren't quite sure what would happen and whether the thing would work. And
Mm.
when we started getting the data in and everything was making sense, it was really kind of exciting to see that nature was, so predictable and sensible and still would work. And of course, the nice thing is that, well, we could keep our jobs, right?
Right. Yeah.
we could have proven that, well, this wasn't going to work. That wouldn't have been such.
Yeah. Right. And then you'd be all sort of out of work.
Well, we would
Well, maybe not, but I know, I understand that was a joke, but still. But do you think you'll see that sort of amazing advances in the future as well? Or like, is there a Moore's law for quantum computing, or is it going to be even more amazing, or is it going to be less amazing? How's that going to look?
I'm feeling very optimistic. Things are working. There are things we have to fix, but things are going well, and we just have to keep at it. And, I would say, in terms of like funding quantum computing and whether the world should be working on it, it's working well enough. So we definitely need to be researching it very, very seriously. It's hard, and like all things, it may not work. You don't know that when you're doing science. But it's working so well that it's great that there's this big effort going on right now to help figure this out and make a quantum computer. It's very much justified.
Do you ever think in sort of moral terms about the future? Like, is this technology going to be used sort of more for good or more for bad? Because obviously, if you're helping out with chemistry, you're probably going to be able to make new medicines, and some other people will probably make new weapons out of it.
Yeah, computers. Look how great computers is for society, and
Yeah.
even things as like it's reprogramming our brain or stressing us out or something. There's always pros and cons of everything we do, and
Right.
I think people need to think carefully about that. Clearly.
Do you ever think about that? Like, do you ever think about sort of the
about it? But I guess I'm have to be an optimist to work.
right to work with it? Yeah.
And then, my concern is always, well, are we going to get it to work, or are the people funding us going to give up and
Yeah.
we have to do something else or lose our job? But my sense is, for example, it's going to be more scientific and technical computing, and that generally is going to help humanity. There are quantum resistant codes out there, so by the time we have a quantum computer, people will figure this out, and internet security will be safe.
Can I ask you, what do you build these machines out of? Like, are you building them out of similar materials as normal computers, or are you using any sort of rare earth materials? What are they made out of?
So the actual qubit chips are made on a silicon wafer, but
Okay.
silicon wafers mostly because it's cheap and very, very, low defects, very well made. And then the superconducting circuits we build out of it is aluminum, okay, which is a very
Really?
common material. You can evaporate it, and we might use indium and sometimes maybe niobium, but none of those materials are very rare or expensive. It's the cheapest thing, and even if it was, the volumes we would use would be so small that it's not a problem. Now, and of course, to cool down this, to get it to low temperatures to work, we use a lot of copper and stainless steel, and I think there's some other rarer things. But again, there's nothing unusual about that.
I'd like to sort of end with a question about the future. What are you getting into next?
Yeah, so I left Google about 2 months ago and been taking a little bit vacation. I guess if you call it a staycation. But at the same time, there's been a lot of inquiries for me, and I have some new ideas. And basically, what I'm thinking about is, what are things I can work at just so that the whole field can build a quantum computer. That's always what I wanted to do. And, now there's kind of more opportunities with different people to build a quantum computer. So we'll just see what happens. But something interesting is going to happen. That's for sure.
Yeah. Well, thanks a lot. This was the first episode of Stir Fried Fascination. The podcast is made, woven, researched, and glued together by me, Rasmus Anderson. Special thanks to Bram van Langen and Lasse Nilsson for their support, feedback, and helping making up crazy questions. If you like the podcast, don't forget to like, subscribe, and tell your friends. And your enemies. After all, they might like it too, and then you can be friends again. This way, you'll improve the podcast and the world. Thanks for listening, and see you in the next one, which is going to be about cerebrums, drugs, and rock and roll.